We can detect sound by feeling vibrations, and that's because the vibrations manifest in air as differences in pressure. So what we're actually feeling is a difference in pressure. Sound is produced over a range of frequencies from infrasonic, which is below 20 hertz, which is too low for humans to hear, to audible frequencies, to ultrasonic frequencies, which are frequencies above 20 kilohertz. And those ones are used for sonograms, which are the things that we use to see babies. And this information is important because it's allowed us to develop sonar technologies, such as submarine radars, fish and depth finders, and there are natural animal echolocations like dolphins and bats, and we have since used that to start creating canes for the blind, applying the same technology. It's a pretty neat technology. There's lots of information out there about it. As you've learned in previous lessons, sound speed can change depending on what it's traveling through, and even depend on the temperature. So specifically sound in air, because that's when it's still going to be relatively audible to us, changes with temperature as well. So that sound, which we're using here, Vs, is 331.6 meters per second plus 0.606 meters per second per degree Celsius times the temperature in Celsius. So we've got a quick example here. If we're in room temperature air that's 20 degrees Celsius, how quickly does sound travel? So all I have to do is plug in the 20 degrees into my equation, and I'll get an answer out. Plug that into my calculator, and it turns out that it is 343.7 meters per second. So therefore, sound travels at 343.7 meters per second in room temperature air. You may have heard the phrase Mach number before, and may even have an idea of what it is telling you. Mach number tells us how quickly an object is traveling relative to the speed of sound. So the Mach number, we use m, is the speed of the object divided by the speed of sound. So Mach 1 means that the object is traveling at the speed of sound. An object that is breaking the sound barrier is traveling faster than sound. And I'm going to show you below here what those waves will look like as the object is traveling. So if the object is stationary, and this blue dot here represents the object, so the sound waves are moving out uniformly around the object. There's nothing special about it. Now if my object is now moving, and it's moving at less than the speed of sound, and again the blue dot is my object, that means that as the object is moving, let's say it's moving this way, as the object is moving, it's kind of keeping up with its sound, or it's at least closer. The sound waves are going to appear closer in front of the object than they are behind, because it's moving toward these sound waves. Oops, that was a terrible last one there. Shouldn't be overlapping. Okay. So since it's traveling that way, it's closer to those wave fronts there. So you're going to hear the sound and then see the object. Now, if the object and sound are traveling at the same speed, that means the object and the wavefront are going to be at the same position. So the wavefronts are just building up in the same spot. It's all traveling at the same speed. We're still going this way. Okay, we're doing all of them going to the right. And the last one here, the object traveling greater than the speed of sound. So that means the object is now in front of each of the wavefronts that it's created. So it has waves that are behind it. So this object will appear before you can actually hear it. So you can kind of see that it would form this kind of funky, almost cone shape behind it. So depending on where you are relative to the object, will kind of show you where the sound will hit. So if you're standing here, the object obviously has to move even further before this sound front is going to hit you. So this object is going to be past you before the sound is past you. And the last slide for this lesson here is on sound intensity. Sound intensity is what we perceive as loudness, so it's what we perceive as volume. The amplitude of a longitudinal wave is directly related to the amount of pressure that is created. And this is a little equation that can show pressure. Pressure is force divided by the area that it covers. So it makes sense that amplitude is related to our perceived volume. Okay? So the intensity is the rate at which the energy is transferred, which you should know as power from the previous unit, over an area. So intensity is P divided by A, which is power divided by the area. So that is measured in watts per square meter. Since sound travels out in every direction, the area the sound is covering is a sphere, right? It's 3D, it's going out everywhere. So that means that the areas we're looking for is related to a radius. Humans can detect sound anywhere from 1 times 10 to the negative 12 to 1 watt per meter squared. So it's all these really tiny numbers. It's probably not something you've seen before, and that's because intensity is more commonly expressed in decibels. So that's the unit there for decibels. Sound exceeding 100 decibels for any length of time can cause hearing damage. Damage at a rock concert, which is typically 110 decibels, can begin to cause damage in as little as 2 minutes. It's an important thing to know and understand, and that ringing you sometimes get in your ear after experiencing loud noises is your ear telling you that it has had some damage done to it by being exposed to loud sound.